entropy of my system to go down, so that then I get advantages such as more cost-effective applications, faster deployment, flexibility, and all that. And that is really the ideal world. I've been working with containers for about 3 years at this point, and what I found out is that most of the time, this is the real experience with container. This is what really happens, in my opinion, with containers, because you find out that containers now put one further layer of isolation between you and your processes. They are scheduled everywhere, they move around, and very important, they talk to each other using these crazy virtual layers of networking stacked one on top of each other. So again, I have had less than ideal experience with containers, and the industry standard response to this need of the community has been essentially to come up with cluster orchestrator. So software components that can abstract away the complexity of maintaining and operating your containers in the infrastructure. So Kubernetes, or Mesos, or Docker Swarm, or whatever you want to put, they take essentially the task of getting your containers as an application developer and scheduling them on your infrastructure using some higher level semantics that you can reason with. So ideally, you don't have to interact with containers that much. And that is always fine until your application works, right? Because when it works, Kubernetes does its job and does its job very well. But at some point, your application will fail, or you will have to troubleshoot it somehow. And it doesn't matter that Kubernetes is handling it for you. You will still have to face yourself with your containers. And so you will have to struggle with the fact that containers are isolated. So you have to face significant challenges when accessing the application inside them. You have minimal runtime, so you don't have all your tool belt of system troubleshooting tools installed in your containers. And they are all moving around. And what I am describing is really not just a marketing pitch or some sort of propaganda because I work for a monitoring company. It's a real need. For example, while I was preparing this presentation, I looked on the GitHub issues for Kubernetes, and I found this one where this guy from the Kubernetes community said, yeah, there is a bug. We have clearly a 20-second timeout on something, but sadly, there are not many debugging tools available in BusyBox, obviously, because your containers is extremely minimal. And then it goes on, if you're willing to dig this further, add this new container and do this sort of random commands. Awful. It has to be much better than that. And so in my use cases, I am going to essentially use Sysdig, not surprisingly. And why Sysdig? Sysdig wants to be really the troubleshooting and debugging tool that you have to enhance your Kubernetes experience. But you can replace essentially Kubernetes with anything that schedules containers. So this is the use cases I'll show will be focused around Kubernetes, but it's really not Kubernetes specific. What is that needs to be said for essentially the integration between Sysdig and Kubernetes? Because it might seem that Sysdig just works with system calls, so obviously it's going to work with Kubernetes. As you have seen, and as Luca showed us in his first presentation, all the Sysdig events, they come from the kernel, and then they enter in the state machine where you are able to filter them by specific containers and all that. With Kubernetes and Sysdig, we have Sysdig connect to the Kubernetes API server and fetch the data, the metadata about how your applications are scheduled. So in Kubernetes, you don't deal with containers. You deal with pods that are theme wrappers around containers. Then pods are usually handled in some sort of deployment, which is like an auto-scaling group for your containers that makes sure that you always have a minimum amount of replicas of your containers up and running across your cluster. So Sysdig fetches all that information and makes it available to you inside Sysdig as Sysdig views or Sysdig filters. And as you will see, when you actually do troubleshooting, that becomes quite useful. And so let's, after this very short introduction, let's start about the troubleshooting use case that I have here. I have a couple. They will take a little bit of time going through it, but I think they are very interesting. So the first one is about Kubernetes services. As I said, Kubernetes takes care of taking your containers and scheduling it for you. But it doesn't only provide that. It provides other building blocks for your application, and one of those is the very powerful service discovery. So Kubernetes allows you to create your containers. Then it allows you to create a service on top of that container, and the service works like this. You link a service with your underlying group of containers, and a service will generate a virtual static IP address that is routable within the Kubernetes cluster. Now, every time within the Kubernetes cluster from another container, you reach out this virtual static IP address, it will be automatically routed towards one of the underlying containers. So even without knowing the actual identity of your services, you are able to access them using this static IP address that Kubernetes provides, some sort of easy to discover load balancer. And not only this, but since remembering IP addresses can get, of course, very complicated, Kubernetes also allows you to give to your services a name, and this name will be a valid DNS entry in your cluster. So whenever you try to resolve this service name as a DNS request, it will be automatically resolved to the IP address of the service so that then you can connect to it and be routed to one of the underlying pods. As you can imagine, there's quite a bit of machinery going on under the hood. And as it was said today in the first talk, it's very, very useful to understand what's going on and just learn to appreciate how things work under the hood, because it will become useful when you are actually doing real troubleshooting. So let's start with this. Again, if you cannot see in the back, let me know. I am going to create these Kubernetes resources. So I have a namespace over here. Again, a namespace is the highest level entity in Kubernetes. So I'm creating a namespace, and inside this namespace, I'm going to create a service that is called backend that will listen on port 80, and then I'm going to link this Kubernetes service to this deployment. Again, a deployment is an auto-scaling group of containers. You can think about it. And in this case, I'm saying this deployment will need to have 3 replicas of the nginx 1.10 container. All right? So I'm deploying this to the cluster, and this is really as easy as doing with kube control, create, and I specify the YAML. And this will create me all the resources. You can see that it will create the namespace, the service, the deployment, then creates also Redis. We'll see later what Redis is used for. So now I can use kube control to describe my service, and it will show you that my service, named backend, has a IP address. This is this one, and this is the static IP address, and it's automatically routed to one of these 3 underlying pods. Now, how do I see this magic in action? I can do this. I can create an interactive pod inside my Kubernetes cluster. And so over here, hold on. All right. So I can create, with this kube control command line, I can create a client that runs the curl Docker image inside my namespace that I just created. So it will drop me in an interactive shell. And look, if I do curl backend, automatically, I get a response from one of the underlying nginx containers that Kubernetes scheduled for me. And I didn't have to know the identity because I just used the DNS name. Now, how does all this work? To see how this all works, I'm going to use Sysdig and sniff at the system level all the machinery that's going on. So I am going to go into this other shell, and I am going to run this command line with Sysdig. First of all, I'm going to choose to print the Kubernetes fields in the standard output. Then I'm going to enlarge the I/O buffers because I'm going to need them. Then I'm going to choose to see ASCII output and don't resolve ports. So this was a little bit of a boilerplate. But now the fun part is I want to look at the network activity of my namespace. So with Sysdig, I can use a filter, which is file descriptor, type in IPv4, IPv6, and, this is the fun part, Kubernetes.namespace.name equal critical app. See how Sysdig is able to understand the semantics of Kubernetes, which is what I needed for this troubleshooting. And then I'm also going to put or process name equals skydns. You'll see in a second while I need it. For the moment, just trust me. And if I run this, now Sysdig will sniff everything that's going on in the system. And so if I repeat my curl backend, I see a bunch of stuff that I can then go and analyze to take a look at what actually happened. And it's quite interesting. I hope you can see in the back. Again, if you can, just raise your hand because it's very important that you are able to see everything. So I see at the beginning curl, which is in this container, on the client pod. See how by putting the PK format, I am able to see the name of the Kubernetes entity. That does, of course, a DNS resolution. So the first thing that it does is contacting this IP address, which is the IP address of my virtual machine, on port 53, and then it sends the DNS request. The DNS request, we can see it in plain text over here, is received by SkyDNS, that is the DNS server that lists on port 53 on my machine. This is the DNS server implemented by Kubernetes. And this is the DNS request. Look at how it is backend, then there's critical app, service, cluster, local. So somehow curl understood that backend was not a fully qualified domain name, and it appended a bunch of crap on top, to make it a fully qualified domain name so that Kubernetes could actually resolve it. Now, the ball is in the SkyDNS court because it needs to resolve this DNS entry to a proper IP address. And how does it do that? In Kubernetes, the source of truth is stored in etcd. Etcd is a distributed key-value data store that contains all the settings. So we can see that SkyDNS starts doing a connection towards etcd because we can see the port 4001. If I didn't filter just for my namespace, I would have actually seen etcd. But then it sends, we can see it sends a HTTP request, because etcd is HTTP-based, asking for the key for backend, critical app, service, cluster, local. So this is how SkyDNS essentially tries to resolve the magic DNS name. It translates it to an etcd request, and etcd, of course, knows the detail about my service, and it replies over here with an HTTP response that contains, among other things, this, the IP address of the service, 10.3.0.220. This is the IP address that it's actually routable in my Kubernetes cluster. And so this IP address gets then packaged as a DNS response, makes its way through curl, and curl over here, we can see that it does a connect, always in the other pod, it does a connect on the virtual IP address on port 80, and then it sends to it the HTTP request, which is the one that I sent from my command line, right? Get slash. And let's see how this same HTTP request is somehow intercepted by the nginx process, which is in another container in one of the backend pods. What is interesting over here, if you pay closer attention, is that look at how nginx accepts the connection, and this is the destination address of the connection, 10.17.0.5, but curl connected to a different IP address, which is the magic IP address, 10.3.0.220. So the same connection has been somehow hijacked into the actual IP address of the pod. And this is where really all the load balancing feature of Kubernetes comes in play. And this is done by IP tables. It's very simple. If you've ever dealt with IP tables, you just go in IP tables and you take a look at the network address translation. And you will see that Kubernetes puts a lot of stuff in it, puts a lot of network address translation rules, and we can see mine that says, hey, whenever you see traffic that goes to this IP address on port 80, make sure that you route it towards this IP tables chain. And this IP tables chain contains 3 rules, 1 per every pod that I have, and you can see how IP tables set a probabilistic rule, and you enter in the first one with 33%, then if it fails, you enter in the other one with 50% probability. And this is how the essentially stateless load balancing is handled by the kernel. So Kubernetes completely defers this to to the kernel. And that's why you see from the system call point of view, you see the tuple of the TCP connection being different. And once this happens, pretty much everything else is straightforward. So we see nginx that does an HTTP response, and then the HTTP response makes its way to curl, which receives it from the network. So we have been able to shed some light on essentially the tricky parts that Kubernetes uses to implement services. So dynamic translation of a DNS request into an etcd request, and load balancing at the kernel level using IP tables. Now, you will probably be thinking, all right, seems that everything works fine, so nothing went particularly wrong. But since I am a very thorough engineer, the first time I implemented this, I followed the Kubernetes guide, and the Kubernetes guide said that every service in Kubernetes gets a DNS name that is under the form of service.namespace.service.cluster.local. So since I wanted to avoid any ambiguity, in my code, in the original curl code, I put the fully qualified domain name over there instead of just backend, because, right, why not? So that I avoid entropy once again. And this is what happened. So I put critical app, service.cluster.local, shoot. I get curl that hangs in there for 10 seconds, and essentially, not only it hangs in there for 10 seconds, but then it correctly sends me the reply. So as a distributed engineer, that's the worst thing. You want things to fail. You don't want things to take 10 seconds and then succeed. That's horrible. So I am going to use now the same sort of troubleshooting that I did in the first use case to figure out what's happening over there, why the fully qualified domain name didn't work. So I'm going to be using the exact same command line, except that this time I'm going to create a Sysdig trace file so that I can then passively analyze the input without having to replicate it any time, which is very powerful. As Adam has said at the beginning, you don't want your troubleshooting tools to harm your processes. And that's the perfect way. Like you're in production, you just sniff it passively, and then you analyze it on your laptop. So if I do sysdig -s, let's enlarge the buffers. If I do this, now Sysdig will going to be saving on the trace file everything that's happening in the system. And I repeat my horrible issue over here. I wait until it succeeds. Again, it takes about 10 seconds. And once it succeeds, now I have a very rich trace file that contains all the activity that went on in the system. And then I can explore it. Again, I'm starting exploring it with the same exact command line that I used before. So I'm just going to go over here and read the trace file. Once I read it, I see a bunch of stuff, and I can start analyzing it from the beginning, trying to spot the differences. We can see that the beginning is pretty similar. Curl does the connect to the DNS server, and SkyDNS receives the DNS request, but something immediately sounds odd. The DNS request is much longer. We have backend critical app service cluster local, and then we have again critical app service cluster local. So it seems like because of maybe some resolve.conf misconfiguration, curl didn't understand that I already passed a fully qualified domain name on the input. And so it tried to patch it in some way by appending the search domain one more time. And this request gets essentially propagated verbatim to etcd over here. So you can see that service cluster local is appended twice in the whole etcd request. And of course, etcd says, no way, I don't know what this thing is. In fact, it returned an HTTP 404, not found. So etcd gives up. I don't know what this service is. You're passing me a bunch of stuff. So then, this essentially not found gets its way again over to curl. But curl doesn't give up. And curl tries one more time with a DNS request which is similar. It's backend critical app service cluster local, but this time it just appended service cluster local. So we are missing in the appended domain critical app. So it seems like curl is trying desperately to append different search domains in order to get the right one. But of course, this one fails as well. We can see that it makes its way to etcd. etcd reply with 404 not found. 404 not found is propagated as a DNS response to curl over here. And then curl tries essentially one more time. This time with an even shorter search domain, backend critical app service cluster local dot cluster local. So we just have 2 more tokens appended. And this one fails as well, again, with a 404. So it might seem like to the untrained eye that we found the issue because we said, oh, yeah, there's a bunch of inefficiencies that are going on over here. But it's not true. Look at the timestamp. This last etcd request happens at 49.61, but the initial request happened at 49.60. So overall, this whole inefficiency took less than 10 milliseconds. That's because every component is living in my local machine. So maybe this will just cause more disruption if I were on a WAN where I had etcd somewhere else. But this is really not my case, because here I'm looking at something big. I'm looking at 10 seconds of timeout. The answer is over here. After this last DNS request, SkyDNS tries one more time, curl tries one more time with this new URL. Backend.criticalapp service cluster local dot local domain. This dot local domain is something that is not being recognized from SkyDNS as being a valid domain name for Kubernetes. And so instead of going to etcd, it decides, oh, I need to forward this dot local domain request to my upstream DNS server, right? And in fact, we can see that SkyDNS then contacts my upstream DNS server, which has another IP address, probably that was discovered via my DHCP setting, and it forwards the DNS request to my upstream DNS. And notice how if you look at the timestamp, then it stays hanging for 4 seconds, between 49 and 53. So we are spending 4 seconds waiting for the reply for the .local domain request, which of course is probably just thrown away from my upstream DNS server because .local domain is not a very mainstream domain name, right? So a DNS server has all the right to ignore it. And so we are spending 4 seconds. And then SkyDNS tries one more time. We can see over here that it tries to send the request one more time. And in fact, we go from .53 to .57. So we spend 4 more seconds. And then we spend 4 more seconds once more. So overall, we spend 12 seconds in trying to resolve a DNS request that wasn't even there, like for a domain name that doesn't exist. And then finally succeeds. Why succeeds? Because as a very last resort, curl decides to, okay, whatever, I'm just going to stop trying to patch things, and I'm just going to pass the domain name verbatim as you passed it from the command line. So you can see backend, critical app, service cluster local. And this is perfectly resolved by etcd. In fact, etcd returns the IP address, and after that, all the request goes through extremely fine. You can see how the HTTP request goes, gets captured by IP tables once again, and gets handled by the nginx pause and makes its way over there. So by looking at things at the system level, I've been able to see that I clearly have 2 issues. The first one is that curl didn't trust me when I provided a fully qualified domain name in the command line. And the second one is that that .local domain made its way into my containers, even though it should have never been there because it's not routable within the Kubernetes cluster. Good troubleshooting. If you have been this far and you've already done network troubleshooting before, you will say, why did you use Sysdig? I could have used TCP dump. TCP dump has a nice DNS decoder that shows me the DNS request and response in a user-friendly way. My response to this is, first, good luck in running TCP dump in your container, because most of the time, actually, 100% of the time, you don't have it in your tool belt inside your Docker image. And second, even if you want to run it outside your container, good luck finding the network interface matching the network namespace of the container that Kubernetes scheduled it. But these are weak motives. I understand why some will be skeptical. I mean, TCP dump is a great tool. So the real reason is that I'm not done with the troubleshooting, because now the natural progression of my troubleshooting is, let's take a look at resolve.conf and let's see what was in there. But my container could have been long gone because this was a production issue. But hey, I have a Sysdig trace file. So I can just use the exact same command line and strip away the filter on the network activity. And now we are talking. Now we see a bunch more stuff, including the resolve.conf as it was read by curl over here. Because, of course, the libc linked inside curl read at runtime the resolve.conf. And the resolve.conf shows us exactly the answer to those two issues. The first one, you can see all the search domains that are appended, and you can see how it's stripping one token every time. And then at the end, we have the .local domain. So this answers why we were seeing those different DNS requests, those 4. And then also the last option, options n.5, will show you why curl didn't trust me when I gave it already a fully qualified domain name. It didn't, because n.5, if you read the man page, means whenever you give a DNS resolution for a host name to the libc with less than 5 dots, I will not treat it as fully qualified domain name, and I will try to first append all the search domains into it. So this was the reason why. There are very good reasons why, of course, Kubernetes put it n.5, the biggest reason being so that I can just type curl backend. But clearly in this case, because of my local domain thing, it screwed things up. And there is one more thing that I can answer, which is why exactly local domain ended up in there? Who screwed up so badly that injected this wrong local domain inside my container? And probably the culprits could be two, right? Could be Docker during the container creation, or it could be Kubernetes when it instructed Docker to create the container. Let's take a look with Sysdig. You will see this thing will pretty much amaze you. So I can take the exact same command line as before, but now I can look. Since I know that all the control plane between Kubernetes and Docker is handled by a Unix socket, I can now filter for Unix sockets. And look at this. Since I'm interested in all the control requests that contain local domain, I can do evt.buffer contains local domain. So now I'm using Sysdig as a grep for your entire system. I'm actually going to use the echo file descriptor chisel so we see some nice colors. Oops. What did I do? Oops, I missed a space over here. And if I create a new client, now I will see over here, okay, oh, hold on. I think there's some, okay. I put IP Unix, which is wrong, right? Sorry, guys, working on this small screen is a pain. Okay, here, local domain, and this will show me all the activity that was actually intercepted during the control plane and just the activity that contained essentially the local domain token. So I can see that Hypercube, which is part of the Kubernetes control plane, wrote on var run docker.sock a post to container create for creating my client container, which contains a bunch of stuff, but most importantly, it contains the local domain token over here. And so we can see that one of the options of the JSON was the DNS search, including all those four search domains. So the culprit in this case was clearly Kubernetes. Really, it's mine because I'm sure I misconfigured my system somehow to handle the local domain. But this should be the final answer as to why I use Sysdig, because I've been able to look at things not only from the network point of view, but I went to the file, and then I went to the Unix sockets. And this was really across containers. I've been able to see inside the containers from outside the containers. So this was the first troubleshooting use case that I had. I have a shorter one, and this one. So again, this was the thing I was telling you about, the frustrating timeout by the DNS request. The other one that I have in mind is rolling deployment. Kubernetes not only takes care of scheduling your containers and making your containers easy to discover, Kubernetes also takes care of making sure that you can update your application with as minimum disruption as possible. So when you create a deployment and you choose, okay, I want to upgrade the image for my deployment because I shipped a bunch of bug fixes, Kubernetes will make sure to bring up the new containers and making sure that they are healthy before bringing down the older containers. And this is essentially the concept of rolling deployment. It's extremely powerful. And I want to show you what happens when it doesn't work. So over here, I'm using the same infrastructure as before, but I am deploying this other additional component, Health Checker. Health Checker is a little component. It's a Go application that I wrote that essentially periodically checks the status of a Kubernetes service, passed as a command line, in this case backend, and then it reports its status onto Redis. It essentially reports the service response time. So if I deploy these on my machine, Health Checker, And now I use, for example, Sysdig, just so we see a little bit more things. And then I go to the Kubernetes pods view. I am able to see all my pods, all my containers, and the health checker over here. If I press F, Sysdig is able to dig into the Kubernetes essentially containers and take a look at the log. So you can see that my service is pinging it, and then it's returning 17 bytes, and it tracks the response time. Very efficient response time because everything is local, obviously. And if I want to see how things work, I can use the echo mode, for example, and I can see over here how all the I/O that my thing does. And so I can see that my health checker talks, obviously, to the virtual static IP address of the service. It does the HTTP request, and then it gets the HTTP response, and then it prints on screen the service, the log line, and then it goes into Redis and saves inside the key backend the same response time. So this is very cool. Let me show you also how it looks like if you look at something a little bit more creative. This is Sysdig Cloud. It's just essentially a distributed extension to Sysdig. And here I can observe my namespace in Critical App, and I can see all my containers, how they are sliced by the deployment and by the individual pod and by the individual container. And then I can see my health checker. And notice what cool it is, that if I click on my deployment, and then I look at something such as the topology map, I am able to see in real time how Kubernetes is making the whole thing work. So I can expand my namespace, and look at how the health checker is talking to the backend deployment and to the Redis deployment. And I can expand this, and I can see how the IP tables thing work. The gray box is the essentially virtual entry for the service, and then I can see how, you can see that how IP tables routes every second. You can see how essentially the link changes and highlights a different second every single different backend pod. And this is how the health checker works. And I can expand that, for example, and take a look at the individual container and processes. So this is pretty cool. But what I wanted to show you is this other thing, which is the rolling deployment. As I said, my thing is an extremely critical application. So if I do Sysdig, and I keep taking a look at the Kubernetes logs, and then I do a rolling update, nginx over here. Here I'm deciding to bump, with kube control, I'm deciding to bump the image of my deployment to one new version of nginx, 1.11. If I do this, Kubernetes will create under the hood new containers and will bring them up, and see how the logs in the lower portion of the screen never report an error because of the rolling deployment. This update doesn't cause any service disruption. And if I don't believe that I have a rolling deployment, I can go, for example, once again, in something like Sysdig Cloud, and I can track a metric like the container count. Okay, the resolution is extremely small. I can take a look at a metric like the container count, and I can see that my monitoring system is putting me that there has been some scaling activity from Kubernetes. And then for one instance, the container count went to 4, and then it went back to 3. And this was while Kubernetes was replacing all the containers under the hood. And it's much more clear if I slice the container count for my deployment by a label that Kubernetes puts, which is the template hash, which is the generation ID of my pods that gets updated every time I do a rolling update. And look at how this chart now looks. You can see how the old copies of the containers are being decommissioned, while the new copies of the containers are being essentially commissioned. And these two lines, they meet pretty high in the whole vertical space, which means that there was no downtime. And so, again, you will see why this is particularly interesting, since everything worked fine. Well, it didn't, because in my original implementation, I used something else in Kubernetes, which is essentially a headless service. I lied when I described how Kubernetes services work. Kubernetes services have one implementation, which is the one that works through virtual service IP address, but there is another one, which is called headless service, that works by not providing a single IP address, a virtual IP address, but it works by just exposing, in a DNS round-robin fashion, the underlying IP addresses of the pods. That's needed when, for example, you have a client connection that needs to needs to be aware of the actual IP addresses of the pods. For example, if you use Cassandra inside Kubernetes. So creating a headless service is as simple as recreating all my service by putting cluster IP none. And when I create it over here, and then I create again my health checker, if I describe my service, you will see that the IP is none, and now I just have the IP addresses of the underlying pods. So now my health checker, if I go and take a look, my health checker is still working fine over here, and is logging. But if I do a rolling update, somehow it will break. Error during health check, and it will not recover anymore. And yet, the rolling update completely happened. I can see over here that I can see the scaling activity. I can see a surge. Actually, we even saw a surge to 6 containers. And I can slice them by the pod template hash. And I can see how the new generation went up, and the old generation went down. So the issue in this case was very easy to find with Sysdig, because I went over here, and I can just look at the I/O activity of my health checker container, and I will find over here that essentially the health checker is still trying to connect to one of the old IP addresses of the pods before my rolling update. So what happened is that in this case, I had a client bug, and my Go client, since I was very sloppy, I cached the IP address instead of resolving it a heavy health check, because I said, oh, well, the IP address in the Kubernetes service is fixed, so it doesn't matter if I cache it. But by caching it on a headless service, you essentially disrupt everything. And that's how I found it. And it's pretty interesting because, for example, if you take a look at the bypass that this health checker in the headless version will do if I don't have essentially the headless service, I can just kill my health checker, and Kubernetes will spin up, of course, a new one, which will work just fine. And I can go, for example, in my monitoring system and taking a look at the map. And you can see how this time, essentially, the map is fundamentally different. Notice how the health checker container, is directly talking to one of the green boxes. So I don't see the gray box anymore, which was the IP table's virtual IP address. And in fact, this is an extremely sloppy health checker, because the IP address is resolved just once. In fact, you can see how my health checker is just always hitting one of the replicas of my service, and not all of them. And this should essentially give you a lot of things to think about when you're troubleshooting containers. And that was pretty much all I had. We have on our blogs a bunch of other troubleshooting stories on containers and Kubernetes. But other than that, thank you very much for listening.
Thank you, Gianluca. Thank you. If we do have any questions, we've got time for questions. Please raise your hand and we'll bring a mic over.
Hey there, over here.
Oh.
So what you showed is, did you show a Kubernetes cluster that had multiple nodes, or was it all on one machine? I didn't understand how Sysdig is introspecting containers running across a bunch of nodes in a cluster the way you were showing it. So.
Absolutely good question. So for the sake of this demo, I essentially spinned up a Kubernetes cluster that was all on my machine. What happens when you want to do this on a distributed cluster is that if you use Sysdig, Sysdig will always need to talk to the API server, but you need to run Sysdig on the node where you actually want to do the troubleshooting. So in this case, you would have to run Sysdig on the node where the health checker Kubernetes pod was there. If instead you use Sysdig Cloud is already, Sysdig Cloud has essentially been created to solve that problem, and you have this modified version of Sysdig that reports everything from each node into a central location, so that then you can correlate everything in that sort of map. But Sysdig itself, yes, is limited to single node, so you would have at least to at least find the node where your pods were, and then start operating with Sysdig on there. But you will still see all the metadata and all that.
A follow-on to that, are you running Sysdig in a container on the node, or are you running Sysdig at the local level on the node?
The short answer is that it doesn't absolutely matter. Sysdig can run. For sure, Sysdig doesn't run inside your application container. That would be a big sin. Sysdig, and that being said, Sysdig can run locally on your machine if your machine has, a proper runtime, or if you are on CoreOS and such sort of those things, you can essentially run it in a separate container, and it won't change anything. The set of features is exactly the same because the data is always fetched by the kernel. Of course, that container would have to be a privileged container, but it's the same set of features. There's really no difference.
Right. So if you want to have a self-configuring or a scalable infrastructure, you can do the monitoring along with the infrastructure. So as you deploy new nodes, you deploy containers on them with Sysdig.
Absolutely. You could choose to have your own chisel that reports to Redis something, and you could deploy essentially the Sysdig container as a daemon set in Kubernetes that automatically deploys one copy per each node, and you will be good to go. A question there in front.
Thanks for your talk.
Sure.
As you were saying before, if you're using Sysdig, you have to basically use it on a single node at a time, right? Is there any way that maybe you can take like a bunch of traces and concatenate them together and then run Sysdig once and still get this kind of top level like view of all of the processes like together, or like?
So at the moment, with the same Sysdig command line, you can specify multiple times the -r flag, so you can read multiple trace files. But it's not the same thing as reading, as merging the file, because if you run a chisel, you will still get one chisel output per trace file. But that being said, that's really an implementation detail. Someone, either us or in the community, should come up with the same thing that in the network world you have. It's called merge cap, that will just take many Sysdig trace files and create a single one, and that will just work. And of course, then you will be able to act with a single filter, see all your infrastructure. Yeah, definitely. It could be, but we have a bunch of stuff in the initializer block or the thread list, so that's why I put my hand forward. I don't want to promise anything that doesn't work. Question?
Hello. Yeah. So you used Kubernetes as a container orchestration system, but there are like other container orchestration systems as well. Does the demo that you provided, is it like independent of the container orchestration system, or did you kind of like have to deal with the specifics of Kubernetes?
So the short answer is it's absolutely agnostic, because wherever you can run containers, Sysdig will just work. If you want the cluster orchestrator filters, at the moment we support Kubernetes and Mesos. Most of the time, though, you will end up finding that your cluster orchestrator, even if it's completely obscure and not mainstream, it's still forwarding some labels inside your containers, so you can still use them inside Sysdig, even if Sysdig doesn't provide official support. Of course, things specific like the service discovery that I showed, those are really Kubernetes specific. Mesos does something completely different from the load balancing, or even Docker Swarm. They use different facilities. But the idea that I wanted to convey is that you can still do it. Like, if you know your system, then you are able to effectively troubleshoot it, even if it's in a container.
Time for one more question, if anybody has one. All right. Thank you, Gianluca.
Thank you.